Okay, we're going to be looking at section 1.5 polynomials and factor, and I'm going to split this actually into two videos, and so not quite as long. So we'll look up until factoring. So we'll do polynomials first, and then in the second video, we'll look at factoring. So here's the objectives. We're going to be looking at some terminology of polynomials, and not just the terminology, but being able to interpret what they're asking for through those terms. Then we'll look at the algebra polynomials. You'll do great with that. That's not going to be a concern of mine. But then the common factoring methods, we're going to bring back some of those factoring methods that you learned throughout Algebra 1 and Algebra 2. So that will be something that we want to get very good at because we're going to do a lot of factoring through college algebra. But let's go ahead and look at some terminology. First thing is a monomial. When we talk about a polynomial, it's interesting is that a polynomial is described by using a definition of a monomial. So we got to sort of know what a monomial is first. But a monomial is a polynomial. It's sort of a weird thing. So a monomial, the prefix mono, you probably know if you know your prefixes, means one. And in this case, what we have is we're just going to call this one term. And now that is not a very formal definition because there are things that look like one term that are not considered monomials because they're not polynomials. And so what we have here is what is not a polynomial. So if you see some certain things, even if it's one term, it's not a polynomial. So I want to describe some of those things. So if you see like a negative exponent, something like that, it is not a polynomial. Now, piggybacking on that a little bit is, let's say we have a variable in the denominator. And so that would not be considered a monomial, even though it sort of looks like one term. And the reason is there's a restriction on the domain. And so polynomials, as we get to it, we'll know that's continuous over the entire real number system. And so any kind of restrictions like here, x can't be 0, creates a discontinuity, and therefore it's not a polynomial. So even though it looks like one term, it doesn't work. Things like square roots. And again, we look at something like a square root and we have a restriction on that. But same goes for if we convert that square root into a rational exponent. So if you see a rational exponent, that would not be considered a monomial. And then obviously anything that's more than one term would not be considered a monomial. But those are really the main things that if you encounter any of those, that is not considered a monomial. And that's going to help us with the definition of a polynomial. Okay, now when we want to find the degree of a monomial, as we look at that, the degree, once we establish that it is a monomial, so it's not one of these four, okay, once we've established that, then we want to find the degree. Now the degree is like its ranking. And so like in the military, each person has a rank. And so that's a little bit what the degree is. And so when we look at the degree of a monomial, we're going to be looking at its exponents. So the exponents have something to do with its degree. Now, specifically the exponents of the variables, or variable if it's a singular. So a variable, and then it could be more than one variable kind of thing. So if they give you something like 2 cubed, well, that's 2's not a variable, so we're not going to look at the cube as anything as part of the degree. So it's just the exponents of the variables. And then what we do to find that degree is it's actually if there's more than one variable, so if it's x squared y cubed, so there's 2 variables with exponents, it's the sum of the variable's exponents. So to find the degree of a single term, what we want to do is first off make sure it is a monomial. And once we say yes, it is a monomial, and we want to find the degree, we look at the variable's exponents and we have the sum of those. Now remember, this is only for a monomial. A single term is the only time that we will add up the variable's exponents. Okay, so we have a tendency to mix up monomials and polynomials because how we find the degree of a polynomial is a little different than how we find the degree of a monomial. So a single term has a certain rank. So we got to figure out its rank. And how to do that is we add up the variable's exponents. Now, what a polynomial is really a collection of monomials. So it's the sum or difference of monomials. And so a polynomial is the addition and subtraction of monomials. Now, it could be a single monomial, which is crazy because when we think of polynomial, we think of more than one. But a monomial is a polynomial. So it could just be a single term. So we can see that like 17x squared right here. This is a monomial, so I'm not really adding or subtracting monomials, but it's still a polynomial, and so that is a possibility. So a monomial is a polynomial of a single term. Binomials, the bi meaning two. So we have these prefixes will help, and then trinomial is three, kind of thing. So just being familiar with the terminology. Now let's go back up to polynomials. Once we've established that, and here's the kicker. When you want to know if something's a polynomial, it has to be made up of all monomials. So in other words, if we have three terms, I need to look at each of those three terms, the first term, the second term, and the third term. All three of those have to be monomials. If any of those three are not monomials, then the whole thing is not a polynomial. So everything, so a polynomial is made up of completely monomials. So once we've established that, yes, each term's a monomial, and how we know that, if we go back, is it's not one of these four, okay? And then we go, okay, therefore it is a polynomial. What we want to do is we want to find the degree of each monomial. So we want to find the degree of this one. And how we define the degree of a monomial is the sum of the variable's exponents. So we're going to do that. And for this sort of example, or this setup, we're going to do it 3 times. We're going to find the degree of the first term. So we're trying to find of each individual term, which one has the highest degree, which one is the highest ranking officer type of thing, because that is going to dominate the behavior or the decisions in the military of what we're doing. So we got to figure out what is the degree of each monomial, and then figure out which one's the largest, because the largest of those is the degree of the polynomial. So we do not add up that degree, and that degree for a polynomial. We add up the degree, the exponents of the variables to find the degree of a monomial, and then we look for the one that's in charge, the largest degree. So the polynomial is the largest monomial degree. So it's the largest monomial degree. Now, in order to find that, it'd be wise to put things in descending order. And they're going to ask you on Hawks occasionally to put things in descending order. Now, what that means, it means we're going to go from the largest degree. So you're going to reorder your terms from largest degree down to the smallest degree. And that would be a descending order. Okay, so you may have to rearrange things. Now, why that's sort of going to be helpful for you to rearrange as well, either in your mind or on paper, is that it also allows us to find the leading coefficient. The leading coefficient is not necessarily the coefficient that's out in front when you are given a problem, because the degrees may not be in order. It's the coefficient once your polynomials in descending order. It's the leading coefficient. So technically, it's the coefficient of the degreed term. So what I mean by that, it's the coefficient of whatever term the degree comes from. So maybe our degreed term is the very last one because they didn't put it in the correct order, so it's not in descending order. So our coefficient is actually going to be found over here, not what's in front. The reason they call it leading coefficient, though, is if you did put it in descending order, it's the coefficient out in front. Okay, so that's why I get it. So if you put in descending order, it's always the one out in front. So you can look at some of the examples of monomials, binomials, and trinomials below, but we're going to move on to some problems. So some of the questions that you may be asked is, how many terms is this potential polynomial made up of? What type of polynomial is it? And the biggest one is the degree. So when we look at an expression like the first one here, we say, well, how many terms is this made up? And terms are connected through addition and subtraction. So what we have is we have one term there, We have a positive y squared, or a y to the 10th there, and a positive 3 there. So what we have is we have 3 terms. So if you want to now the question is that a polynomial? So before I say what type it is, because you can't call it a trinomial unless it's a polynomial. But I don't see any of those issues we talked about. I don't see any negative exponents. I don't see fractions as exponents. I don't see any radicals. I don't see any variables in the denominator. So I should be good. This is a trinomial. And then what we want to do is we want to identify what the degree is of this polynomial, of this trinomial. So what we do is we go back and we look at each one of those 3 terms. Each of those 3 terms have a degree. And to find the degree of a term, of a monomial, it's the sum of the variables' exponents. So the ranking of the first term is 8, 3 plus 5. The second one is 10. And the third one, the degree of a constant, is 0. So you can either memorize that or just to prove that to you, technically what we have is 3 times x to the 0. That's the same thing as just saying 3. We don't write the x to the 0, but it's there, just invisible. And so what we have is the degree is the variable's exponent, which is 0. Now, what we do is our degree is not going to be 18. Please don't add these up. That's we tend to mix up monomial and polynomial degrees. We add up the variable's exponents to find the degree of a monomial. But the degree of a polynomial is which of these 3 has the highest rank. So which one's the largest is the degree of the entire thing, and that would be 10. And we're going to use this quite a bit when we do polynomial work later in college algebra. So it's really important to understand this skill, is that finding the degree, because the degree, this 10 as a degree, tells me a lot about that polynomial. And so knowing what the degree of the polynomial is, it dominates the behavior of the polynomial. So it tells me a little bit about it. Let's look at the second and third example here. Looking at the second example, we look and it has 2 terms. And so if you look here, we have one term that is the negative 3x to the 4th. Y squared. So I'm going to put a box around it just so you can see it. And the positive 5.4, excuse me, x cubed y to the 4th. So we have 2 terms. That's called a binomial. And then what we want to do is we want to find the degree of that binomial. And so to find the degree of the binomial, we want to find each monomial degree. So it's the sum of the variables' exponents. And so what we get for the sum of the first monomial is 6. And the degree of the second one is 7. So the question now holds is we don't add the 6 and 7. We just say which one's the largest. That's the degree of the polynomial. And so 7 is the degree of that binomial. Looking at the last one, we sort of mentioned this with the 3x to the 0, which is 3. When we look at 5, technically what we have is 5, and then out to the side, technically there's an x to the 0. So you don't need to write it, but just to see it. So how many terms do we have? We have one term, which is a monomial. And so we've got that bit of information done. And then what's the question is, what's the degree? Well, without the variable next to it, it's sometimes a little bit more complicated for students because they don't see the variable's exponent. But if I show you this x to the 0 next to it, the degree is obviously the variable's exponent, or the sum of them, and so 0. Or you could just memorize the degree of a constant is 0. So when you see that, you know it's just 0. Let's go ahead and take a look at combining like terms of polynomials. And so again, this is stuff that you're going to be very comfortable with, and we'll pick up very quickly. And so what we want to be able to do is we want to be able to add, subtract, and then eventually here in just a moment we'll multiply polynomials. And so when we have a situation where we're adding or subtracting terms, we want to make sure that we understand what is a like or similar term. And so what makes a term similar is that the variable factors are the same. So we've looked at variable factors before in earlier lessons. So hopefully that helps, but that means that the last name needs to be the same. In order to add or subtract, I sometimes call it the last name rather than variable factors. So we have a numerical factor, which is the coefficient, the number in front. That tells me how many of the item I have. And then the variable aspect of it is like its last name. It tells you sort of what that item is. So we have 1x cubed minus 2z plus 1y squared plus 1z minus 1y squared plus 3x cubed. And so what we're looking for is, do we have any of these variable factors are the same? So as I look through, I recognize that I have a negative 2z and a 1z. And so I don't, and then I also have an x cubed here, and a 3x cubed there. And then what I have is I have a y squared there and a negative y squared there. So I do have some similar terms. I try to mark them with different sort of symbols there. Let's go ahead and combine them. So we're going to put the x's and do those first. And so let's look at these two. So if I have 1x cubed and I'm adding 3x cubed, that means I should end with 4x cubed. Last names don't change, just the coefficients. And so that should end up getting my term for the x's. Now if we go ahead and look at, let's say, the y's, because we usually go alphabetical order, I have 1y squared, and then I subtract 1y squared. You know, that means I have 0y squared, which means I have 0. So the y's are gone. Then what we have is negative 2z, and then we add 1z to that. So the last name doesn't change. All I do is look at the coefficients and figure out how many do I have, which means I have negative 1z. Okay? And so there's our simplified expression combining like terms. So that's what we're going to end up doing. College algebra will occasionally give you the polynomials in this form where you have parentheses. Don't overanalyze these too much when it says add the polynomial or subtract the polynomials. The only thing we want to be careful of is right here. And if that is a subtraction sign, and then there's a quantity to the right of it, something like this, we need to make sure that we distribute that minus sign through as we go ahead and rewrite this. Because I would encourage you to rewrite this without bubbles. And to do that, we may need to distribute a negative. So we have 2x cubed y minus 3y plus z squared x. So the first one, there's nothing to distribute, so they all stay the same sign. Here being a plus sign, it does not change the signs of anything. So the signs inside of my trinomial or my 4-term polynomial over here is going to stay the same. And so 3y z squared and we get to this point. Okay. Now what we do is just like we did before. So I'm going to go a little quicker at this point and get these. So I'm looking for x cubed y's. Do I have any other x cubed y's? And I don't have any more x cubed y's. Now, I'm going to do a little side note. Let's say down the far end, we had like 4yx cubed. These would be like terms. Now, I know they don't look identical, but all this is multiplication, so commutative property would allow me to flip the order. So all I'm looking for is, does anything have the exact same variables with exponents in the term? So don't just assume because the order is different, because we can use the old commutative property to allow us to reorder it, and they would be like. So this one looks like it's done, though. There's nothing else down the row. So I like putting a mark through when I'm done. Now let's do negative 3y. Do I have any other? Yep, there's a positive 3y, and I don't have any more. And those would cancel each other out. 0y, they're gone. Now let's do z squared x. Do I have any other z squared x? There it is. So this is great. Do you see right here where even though it's not z squared x, all I have to do is use commutative property, and I do. So I actually have two like terms. I have a positive 1 of those things, and then I have a minus 3. So 1 banana minus 3 banana is negative 2 a banana. And I'm actually going to write it xz squared because I like my variables alphabetical order. So we're done with those two. And so we're down to really the last two, which you'll notice is sort of solos here. Nothing can combine with those, and so z squared goes, and then 4 goes, and we're done. And then what's in black is our solution. Okay, moving on to a subtraction one. What I mentioned is here we just need to be careful that we distribute the negative when we rewrite. Okay, or as you evaluate these. And so as I look at these, what I have is 4ab cubed minus b cubed c, and then here we go, minus 4, but then we have a plus b cubed c. Make sure to distribute that negative. Now we can look for like terms, and what you'll notice here is that we do have a b cubed c that cancels with this b cubed c, but really that's it. Everything else is its own term. So there's our final answer. Just be careful of distributing that negative. You should be in good shape. Then we move into multiplication. There's going to be two types. The last one, actually, I'm sort of giving you a harder one first and the easier one second, but let's go ahead and look at this. And when we talk distributive property, what we want to do is we want to start with the first term, and we go ahead and distribute it through whatever number of values we have over here to the right. So I'm going to go ahead and write that sort of down here. It's going to get pretty long because we're going to have to do the same thing with z cubed. So I'm going to have 8x squared y, and then when I distribute to the second thing, I get 6, and then I have x squared yz, x squared yz, and then we get 2 times -3, which is -6, and then we get x times x squared. So multiplying powers, you add exponents. And then we got y times y, which is y squared. So there's the 3 from my first one. I'm going to go ahead and put the second one in just a different shade here so we can see the differences. So I'm going to be distributing negative z cubed. And we're just in a lighter color here so you can see the difference. So we have minus 4z cubed, and then plus, now notice here, oops, I'm sorry, we have a negative times a positive. I said plus, but it's going to be a negative. So a negative times a positive is negative. And then we have 3z to the fourth, because we have z times z cubed. When you multiply powers, you add exponents. Now, in the last one, we have negative times negative, which is positive. And then we get 3x, y, and then z cubed. And so there's our distribution of those. Now what we're going to do is just like on the one before, we can look for like terms. So I always just start with the first one and look for any x squared y's. And I don't see any x squared y. So I'm just going to write it first, 8x squared y. Then I look for x squared yz. X squared yz, I don't see any of those. And so we're here. I have a feeling there's not going to be a whole lot of like terms on this problem. But let's just keep going. X cubed y squared, no x cubed y squares. Let's just keep going because I don't think any of these match up. Z cubed, there's no z cubed. Z to the fourth, there's no z to the fourth, and obviously the last one. So really, let me just sort of backtrack a little bit. From what I've discovered is this monstrosity is our simplified expression, our polynomial. So just leave it like that and type it in or write it down. Last thing we'll look at before this video is over, and then we'll pick up another one after, is going to be foiling. And so it's not like something we haven't done. We've already done some foiling because we use conjugates to rationalize denominators, and of that, we only had to do fl. But we've definitely done some foiling. So just a binomial. Now, foiling is simply a method. It's distributive property is what we're doing. And so just make sure that that's something that you can do. I'll go ahead and do this example, and then, if you want to work ahead, that's fine. So 3ab times ab is 3, and now I have 2a, so a squared, and I have 2b, so b squared. Then that's our first. Now outer, I'm going to have 3ab times a squared, so positive 3. Now I have 3 a's, and then a b kind of thing. And then inner, looks like it's going to be a negative because a negative times a positive is negative. Then we have a cubed b. And then for the last one, I have a negative times a positive, which is negative, and it looks like I have 4 of these a's right there. And then what we do is we look to combine like terms. Now, typically, when we FOIL, either they're done, okay, because it could be done, or once in a while, what you have is you could have like the outer and inner are sometimes ones that you can do. I've seen the other ones combined, but definitely the outer and inner you want to keep an eye out for. So we have 3a squared, b squared, and then what we have here is 3 bananas minus 1 banana. And so if we have 3 bananas minus 1 banana, we should have a positive 2 bananas. All right, keep using bananas, but all terms are items, just like anything else that we have. The number in front, the coefficient, is just how many. And so when we see it like that, it tends to hopefully make your life a little easier. But that's going to wrap up for 1.5a, and we'll jump back in and look at factoring in 1.5.